Welcome everyone, my name is Amar Morsi and I'm the chair of this session titled Walls, Embankments and Slopes. A couple of things to note before we get started. You will have the opportunity to ask questions during this on-demand session by clicking on the questions button at the bottom of the video window. Your questions will be sent to the presenters to answer as soon as they are able. To claim PDH credits for this session and any other education session, you simply need to click on the Claim Credit button on the conference homepage. From there, you will fill out the survey for any session that you attend. Please note that you will need to include the verification code shown in this session to verify that you did attend this session and ensure that you receive the proper credits. Please enjoy the presentations. Thank you.
Hello, and thank you for your time today. My name is Drew Loazo. I'm the Engineering Services Manager here at Propex, and today I'll be presenting on the use of geosynthetic wrap face vegetated MSE walls for enhancing public works projects. This is a paper that Stanley Miller, myself, and Todd Larson put together, and is really specific to a product called Pure Wall offered by Propex. For a brief project overview, these were upgrade and expansion projects located within Ramsey County, Minnesota. They both required the installation of a mechanically stabilized earth, or MSE wall. They originally were designed with masonry block wall facing. In the first one, Edgewood Middle School was 190 feet long and 8 foot high and separated the paved parking lot from grass fields below. The second project, Mounds View High School, was about 2,400 square foot of wall face with up to a 15 foot high wall. And the goal of this one was to provide a more flat area along the sloping grade. While the original design used concrete masonry block facing, the general contractor for both projects worked along with the design engineers and school district to discuss substituting an engineered vegetated wall system in place. Ultimately, a geosynthetic wrapped face vegetated wall was selected and utilized. It became a more cost-effective, environmentally friendly, and green solution to the original design. The geosynthetic wrap face vegetated wall is composed of several different components. First is the High Performance Turf Reinforcement Mat, or HPTRM. This is used to wrap the wall faces and provide a durable vegetated face, as well as provide secondary reinforcement to the wall. The second component is the fiber composite braces. These are woven within the HPTRM structure to allow for the construction of the individual lifts without external slit forms. The third component is the use of geogrid for primary reinforcement. These geogrid layers are placed in between the HPTRM lifts and allows for a higher wall height to be achieved. When utilizing a wrap face vegetated wall, there are several different features and benefits that can be achieved. By utilizing vegetation, it is considered a best management practice for improved water compliance as well as water quality. The HPTRM component provides a very high strength, durable material on the face that allows for a vegetated, permeable facing for long-term performance. The bracing that is used internally to the structure means that you don't need any temporary bracing or any metal forms, so there's no corrosion potential for the system. The flexibility of the system also allows for curves to be incorporated and potentially the use of on-site soil. The system is very easily transported and is available in green or tan depending on your location. Both the Edgewood Middle School and the Mounds View High School were located just outside of Minneapolis, Minnesota. There were several walls within the Mounds View High School. This one here we can see on the left-hand side adjacent to the wooded area. When designing for the use of a wrap face vegetated wall, several different design considerations need to be made. First, considering the soil properties here, analysis needs to be ran looking at the sliding, overturning, and bearing capacity of the wall. For this cross-section shown here, with a 250 pound per square foot surcharge for traffic loading, factor safety exceeded 1.3 for these three scenarios. Additional analysis showed that using the same soils and surcharge loading as before, that the global and compound stability of the slope exceeded the 1.3 factor of safety as well. With the design of the wrap face vegetated wall being approved, construction can now start. Here we show the installation of the HPTRM and bracing components around a curve. The flexibility of the system allows for curves like this to be incorporated throughout the cross-section if needed. With various geometries across the site, we were able to incorporate various offsets between each lift to account for the batter needed on each location. As the wall is constructed, each lift is compacted in order to achieve a stable wall. Here we can see the completed installation of the Mounds View High School. The HVTRM component is shown here as the wall lift has been completed prior to vegetation establishment. The wall heights vary from 4 feet up to 15 foot, and for vegetation, the contractor elected to hydroseed the installation post completion of the wall. After about a month's time, we can see the vegetation starting to establish along the wall face. This is in a shaded area, and vegetation will continue to establish over time. Now looking at it almost a year later, vegetation has really started to establish well. You see good vegetation on every single lift, and it's starting to fill in between the lifts as well. Now looking at the Edgewood Middle School, we can see here the wall located just on the outside of the pavement section. The wall here was designed to provide some grade relief and separate the grassed field area below from the pavement section above. The same design criteria was required for the Edgewood Middle School as well. Using the soil properties given provided by the geotechnical engineer record, we were able to look at the configuration shown here with a surcharge of 250 pounds per square foot for vehicle loading, and able to look at achieving a 1.3 factor of safety for sliding, overturning, and bearing capacity of this wall section. Additionally, a factor of safety of 1.3 was met for global and compound stability shown here. This evaluates the soil properties, the surcharge loading, and the configuration of the wall system. As the enhancement project started, we can see the drainage system that's going to be underneath the pavement section here. Once this was constructed and the road was started to build, we can then work on the wall section that will help with grade relief between the pavement section final as well as the grass section below. When constructing any wall, we have to first start with the foundation. Here we show the native compacted soil ready for the first lift to be placed. Once the geogrid is placed first, a small soil layer is placed on top of the geogrid so that there's no geosynthetic to geosynthetic interaction. The wrap-faced wall, the HVTRM component, will then sit on top of this. Here we can see the first lift of the HVTRM and braces in place. Once it's aligned, soil will then be backfilled and compacted so that we have a good competent layer. This process will be repeated each time, with soil being placed in between each geosynthetic layer. We can see here the fill being placed, the excavator placing each load, and then the dozer coming back and placing it and pushing it out. After it's in place, then the compactor is going to come back and provide compaction for the soil. Large compaction equipment like this can be used. As you get closer to the wall face, it's suggested that we use smaller compaction equipment just so we don't over stress the facing of the wall itself. Now here we see the first lift of the wall completed. You see the HVTRM on the surface for the secondary reinforcement. Each final lift will be completed in the same way, where you place each lift with the soil backfilled compacted and the secondary reinforcement as well as the primary geogrid reinforcement for each lift. As the wall height varies, you can step up or step down each lift depending on the need. That way you can work with the grading on site and contour as you need to. For any wall, we want to look at long-term performance. We also want to look at short-term performance. So here we see the wall section completed, but we also see some decent loading on top with the pavement equipment. This allows us to make sure that we can have a good design, short-term and long-term. Now, once vegetation is established, we'll see this start to progress. For this application, the contractor elected to place topsoil and seed within each wall lift. After the construction, it came back and hydroseeded the outside. As you can see, only a few months after installation, vegetation is really starting to take hold. And when you look at it, all you see is vegetation. You see a vegetated, very aesthetically green solution, but it's also a geotechnically stable, long-term, durable solution. Now, after about a year of vegetation, that vegetation is really starting to come in well. We've got the grasses, we've got some native vegetation coming in as well, some flowered areas as well. But again, you get a very aesthetically pleasing, very stable, and long-term solution for this grade separation. From the other side, we can see the same thing. Vegetation is starting to establish well, but we can also see a little bit of the HVTRM coming through. That's normal. Vegetation starts to come through and fill in, but also it shows that we really need durability. Vegetation is what we always want to see, but we also know that vegetation is never going to be constant, never going to be completely covering, and we need a durable HVTRM on the surface so that that vegetation can root in well, but if the vegetation is not there, we still get the same performance, same durability for that wall system. I want to thank everybody who was involved in this project, both of these projects, both the middle school and the high school. We had a lot of collaborative efforts here with the engineers, with the contractors, with the school districts. So thank you guys all for your help. This was a very successful project all around. Thank you again for your time. My name is Drew Loazo. I'm the Engineering Services Manager here at Bropex. We work through these projects on a weekly basis. If there's anything we can do to help answer any questions, provide any design assistance, please let us know. Please reach out. Thank you again for your time.
Hello everyone, my name is Yuqiu Ye. I'm from the University of Kansas, and my supervisor is Professor Ji Han. Today, my presentation topic is method for calculating vertical stresses in limited space geosynthetic reinforced soil walls. In my presentation, I'm going to talk about the introduction, model test results, existing and proposed methods, verification, and summary. GRS walls has been widely used in embankments, slopes, and retaining walls. However, due to the site constraints, there is a very limited space for GRS walls. Footing nodes are generally considered in the design of GRS walls. 2-to-1 distribution method has been proposed to calculate the vertical stress for GRS walls. Multi-model test results show that wall soil fraction had significant influence on the vertical stresses. The 2-to-1 distribution method didn't consider the influence of wall soil fraction. Therefore, the vertical stresses in GRS walls remains further investigation. Our research group conducted a series of model tests for GRS walls. The inner size of test apparatus is 2.4 meter long, 0.45 meter wide, and 1 meter high. The hydraulic jack and load plate were used to simulate the footing nodes as shown in the photo of test apparatus. In the model test, Kansas River sand was used as backfill. The friction angle was 37 degrees, the relative density is 70%, and the dry unit weight is 17.8 kN per meter cube. Punching drawn by Excel PPJ grid was used as the reinforcement. The ultimate tensile strength is 12.4 kN per meter in the marching direction and 19 kN per meter in the crossing marching direction. Our research group conducted a series of model tests for GRS walls. 2 model tests were selected and labeled as test T1 and test T2. For test T1, the backfill width was 0.7 meter, the backfill height is 1 meter, the outside was 0.2 meter, and the reinforcement space was 0.2 meter. For test T2, the only difference was the backfill width, which was 0.5 meter. The earth pressure cells were placed along the centerline of footing. Test results show that those two tests had the similar distribution trends of the major vertical stresses under all the applied pressures. The vertical stresses decreased with the depth and increased with the increase of applied pressures. The influence depth of the footing nodes was almost 5 times the footing node's width, which is consistent with the theoretical solution, such as the bosonless solution. 2-to-1 stress distribution method has been proposed to calculate the vertical stress for GRS walls under the footing nodes. This method assumes that the applied pressures from the footing nodes uniformly distributed at an angle of 2-to-1. Therefore, the effective distance di can be calculated using the equations shown in the right side. And then we can go to calculate the vertical stresses from the footing nodes as F divided by di. And F is the applied pressures, di is the effective distance. In our proposed method, the backfill was divided into n horizontal slices, and the effective length di at every horizontal slice can be obtained using the following expressions. And then we can go to calculate the vertical stresses. We use the footing nodes F times BF times W minus the accumulated friction force along the stable wall and the retaining wall, and then divided by the effective error di times W. F is the applied pressures, BF is the length of the footing nodes, and W is the width of backfill, which is the same as the width of the footing nodes. And for different boundary conditions, the friction force at every horizontal slice can be obtained using the following equations. Here is the verification. Those two figures show that the predicted results from our proposed method should better agreement with the tested results than the 2-to-1 stress distribution method. The last one is our summary. The model test shows the major vertical stresses decreased from the bottom of the footing with the increase of depth to the minimum value at the depth of 5 times the footing width. The calculated vertical stresses using the proposed simplified method were compared better with the major ones in the model test than those calculated by the 2-to-1 stress distribution method.
Hello, my name is Mustafa Rahmani Nishad. I'm a senior engineer at Turkon, and I'm presenting my paper titled Limit Equilibrium Analysis of Geosynthetic Reinforced Retaining Wall Supported Footing. And the co-authors of this paper are Dr. Jihan, Dr. Mehdi Al-Naddab, and Dr. Jaber Mamakani. The outline of my presentation are introduction, problem statement and objectives, stability of GRR walls subjected to footing loading, limit equilibrium analysis, modeling, results, and finally conclusions. Geosynthetic reinforced soil, or GRS, has been successfully used for construction of many earth structures such as retaining walls, slopes, and embankments. Among these structures, the geosynthetic reinforced retaining walls, or GRR walls, have been commonly used for many applications in transportation systems. In recent years, GRR walls have been increasing use as bridge abutment instead of pile foundation. In this technology, GRR abutment walls support bridge beam on spread footings directly on the reinforced field for bridge approach embankments, roadways, railways, which are subjected to traffic load. The major advantages of this technology are to eliminate pile foundations, to reduce the overall cost of construction, and also to minimize bump at the end of bridge. Bumps at the end of bridge usually happens due to the differential settlement between approaching embankment and pile-supported abutments. In these pictures, you can see some reasons of bump at the end of bridge. For example, soil erosion, earthquake, and poor compaction of backfill. One of the Kansas Department of Transportation reports shows in 2019, Kansas had 24,786 bridges. Among these bridges, about 15% of them had a structurally or functionally problems. This figure shows the typical cross-section of GRR bridge abutments with shallow footing, girder, approaching slab, roadway, flexible facing, and reinforced zone. According to the FHWA design guideline, design of GRR abutment walls is considered as a complex geometry and also spatial condition. The left picture shows a bilinear potential failure surface for this kind of abutment when they are subjected to the footing loads. And as you can see, the failure surface starts from the far edge of the footing. Also, according to the FHWA, the tensile force in reinforcements can compute based on the lateral pressure. The right picture shows the distribution of the vertical stress from the footing loading on top of the wall. This method usually calls 2-to-1 distribution method. Although several studies have been conducted to evaluate the effect of the embedment depths of the footing on GRS backfills, limited studies so far have been conducted to investigate the effect of the embedment depths of the footing on the behavior of GRR abutment walls. So the objective of this study is to evaluate the effect of the embedment depth and also offset distance, with the distance between the facing and footing, on the possible failure surface, and also the bearing capacity of the footing of GRR abutment walls with modular block facing. Basically, to design GRR walls, we need to evaluate external stabilities. So to evaluate external stability, we need to check sliding, overturning, bearing resistance, and global stability, as shown in this figure. The GRR abutment walls are subjected to high footing loads that are close to the wall facing. So not only the stability of the GRR walls, but also the bearing capacity and settlement of the bridge footing should be considered in design. The limited bearing methods have been used for decades to analyze the stability of geosynthetic reinforced slopes and retaining walls. Two common methods are Bishop modified method and Spencer method. In this study, we used Bishop modified method. Also, I have to mention, in this study, the ultimate bearing capacity is the pressure at which the corresponding factor of safety using the Bishop method is 1. The limit equilibrium method, incorporated in the research software version 3 developed by the Adama Engineering Incorporation, was employed to determine the potential failure surfaces and also calculate the factors of safety of GRR walls subjected to footing loading by using Bishop's simplified method. However, this paper does not evaluate other aspects of GRR wall stability, such as internal stability, sliding, and overturning. This figure shows the geometry and material properties of the baseline model. To prevent any possible failure in the foundation soil below the GRR wall, the foundation soil was assumed to have high strength value. The model walls had a height of 6 meters from the top of the foundation level to the finish approaching slab. In the model walls, the reinforcement length increased linearly from 8 meters at the bottom with a 1-to-1 slope toward the approaching slab. The vertical spacing of the reinforcement layer was 0.4 meters. The embedment depth of the footing and the offset distance between the back of the wall facing and closed edge of the footing were varied. In this parametric study, one parameter was changed from the baseline, while all others were unchanged. This figure shows the calculate ultimate drain capacity of footing and GRR above the wall versus the embedment depth of footing at a constant footing offset of 1.5 meters using Bishop's simplified method. The results indicate that the wall with a deeper embedment depth had higher ultimate capacity than walls with a shallower footing. For example, the increase of the embedment depth from 0 to 2.4 meters resulted about 25.7% higher footing ultimate drain capacity. This figure presents the location and shapes of potential failure surfaces within the wall at different embedment depths of the footing and the constant footing offset of 1.5 meters determined using Bishop's simplified method. As you can see, the potential failure surfaces began or passed from the center of the footing and developed into the reinforced zone toward the wall facing. The footing with a deeper embedment resulted in a slightly deeper failure zone than that with a shallower embedment. The conclusion between Bishop simplified and the FHW method indicated that the potential failure surface in the wall with a shallow footing determined by Bishop simplified method was close to the surface identified by the FHW method. However, an increase of the embedment depth of the footing, the potential failure surface identified by Bishop simplified method became deeper than that proposed by FHW method. This figure presents the calculated ultimate drain capacity of the footing versus the offset distance of the footing with a constant embedment depth of 1.2 meters by using Bishop's simplified method. The result showed that the wall with a larger offset distance had a higher ultimate drain capacity for the footing than the wall with a smaller offset distance. When the footing was located next to the wall facing with more offset, the calculated ultimate drain capacity was about 138.5% lower than that with an offset of 3.5 meters. This figure presents the location and shape of the potential failure surfaces within the wall at different offset distance that were determined using Bishop simplified method and also the FHW method. The potential failure surface using Bishop simplified method began from the center of the footing and developed into the reinforced zone toward the wall facing. Therefore, the wall with a larger footing offset distance had a deeper potential failure surface as compared with that with a smaller offset distance using Bishop simplified method. When the wall had an offset distance of smaller than 0.5 meter, the potential failure surface proposed by Bishop simplified method and FHW method were similar. However, as the offset distance of the footing increased, the potential failure surface identified by Bishop simplified method was deeper than the proposed by the FHW method. This study investigated the effect of the embedment depth of the footing and also the offset distance of the footing from the wall facing and the global stability of geosynthetic reinforced retaining abutment walls that we call GRR abutment walls with modular block facing. The limit equilibrium program was used to determine the potential failure surfaces and also calculate the ultimate burn capacity of the footing using Bishop simplified method. From this study, the following conclusions can be made. First, the increase in the embedment depth slightly increased the ultimate burn capacity of the footing. Second, the potential failure surfaces identified by Bishop simplified method began from the center of the footing and developed into the reinforced zone toward the abutment walls facing forward. Third, the potential failure surface determined using Bishop simplified method of the abutment walls with a larger embedment depth of the footing were slightly deeper than those with the wall with a shallower footing. Fourth, the abutment wall with a longer offset distance had a higher ultimate burn capacity for the footing than the wall with a shorter offset distance. Fifth, the abutment wall with a larger footing offset distance had a deeper potential failure surface as determined by Bishop simplified method, as compared with the wall with a smaller offset distance. And finally, it's worth mentioning that the limit equilibrium approach employed in this study is only considering force and moment equilibrium. However, this approach does not consider the footing load-induced stress level effect on the soil and reinforcement behavior. So future studies using numerical methods should be conducted to take into account the stress deformation behavior of geosynthetic reinforced soil system under footing loading and verify the results obtained in this study. The first author would like to thank Dr. W. Chinsky at Adama Engineering Incorporation for providing valuable help and advice for the software used in this study. Also, we would like to acknowledge Dr. Robert Parsons, professor at the University of Kansas, for his support. Thank you very much.